Throughout human history, we have gazed up at the night sky and wondered if we were alone. Not just alone as a species, but alone as a universe. Ancient civilizations crafted elaborate stories about hidden dimensions, celestial kingdoms stacked like layers of an infinite cake, and worlds beyond worlds stretching into eternity. In the sacred texts of Hinduism, sages spoke of universes being born and dying in cosmic cycles without end, each one breathing in and out like a living organism. The Greek atomists, particularly Democritus and his followers, imagined an infinite cosmos filled with countless worlds, some eerily similar to our own, others wildly alien and incomprehensible. Even in the medieval period, when religious orthodoxy dominated intellectual life, daring scholars whispered about the possibility that God's creation might not be limited to a single universe. They pondered whether the divine act of creation could have produced multiple realities, each one a testament to infinite creative power. These weren't idle fantasies or primitive superstitions. They were humanity's first attempts to grapple with a question that would eventually become one of the most profound inquiries in modern science. Fast forward to our present era, and those ancient myths and philosophical speculations don't seem quite so mythical anymore. They sound instead like early sketches of an idea that has now entered the realm of serious scientific investigation. Modern physics, with its sophisticated mathematics and powerful observational tools, has opened a door to a possibility that feels simultaneously exhilarating and deeply unsettling. We might be living in just one universe among an incomprehensibly vast number of others. Our cosmos, with all its galaxies and stars and planets, might be nothing more than a single bubble floating in an infinite ocean of realities. For most of recorded history, the concept of multiple universes existed purely in the domain of mythology and imagination. But as humanity's scientific instruments grew sharper and our questions grew bolder, those ancient dreams began their transformation into genuine scientific hypotheses. The journey from myth to science has been long and winding, marked by revolutionary discoveries that repeatedly shattered our assumptions about the nature of reality. For thousands of years, Aristotle's geocentric model dominated human thinking about the cosmos. It was a comfortable, tidy picture of the universe, with Earth firmly planted at its center, surrounded by crystalline spheres carrying the sun, moon, planets, and stars. Everything revolved around us. We were the focus of creation, the center stage of cosmic drama. Then came Nicolaus Copernicus in the 16th century, whose careful observations and mathematical reasoning revealed a truth that would forever change humanity's place in the cosmos. The sun, not Earth, occupied the center of our planetary system. We were not the hub around which everything turned. We were merely one planet among several, orbiting an unremarkable star. Centuries later, in the early 20th century, astronomers believed they had finally mapped the full extent of existence. The Milky Way galaxy, they thought, was the entire universe. Everything that existed, all the stars and nebulae visible through their telescopes, belonged to this single grand structure. Then Edwin Hubble, working at the Mount Wilson Observatory in California, made a discovery that would once again explode the boundaries of the known cosmos. Those fuzzy patches of light scattered across the night sky weren't nearby clouds of gas within our galaxy. They were entire galaxies themselves, each containing billions of stars, separated from us by distances so vast they defied intuitive comprehension. This pattern of surprise and expansion has repeated itself throughout the history of astronomy. Every time we think we've finally reached the edge, science pushes the boundary further outward. And in our own time, just when scientists believed they had successfully mapped the limits of the observable universe, another idea began to germinate in the minds of theoretical physicists. This idea quietly suggested that our cosmos might be only a single layer in an incomprehensibly vast cosmic hierarchy. The physicist who would eventually articulate this vision most clearly spoke of multiple levels of universes, each stranger and more expansive than the last. And here's what makes this story so compelling. None of it was pure speculation or wishful thinking. The ideas emerged from rigorous mathematical frameworks, from careful interpretation of experimental data, from taking seriously the implications of our most successful physical theories. So, the question transforms. It's no longer simply, is there another world out there beyond our own? The question becomes something far more profound and far more challenging to human intuition. How many universes could there possibly be? In the quiet Swedish town of Täby, a young boy named Max grew up immersed in two seemingly contradictory worlds. His father, Harold Tegmark, was a mathematician of the old school, stern and precise, who believed that everything in nature, from the delicate symmetry of snowflakes to the spiral arms of galaxies, could be understood if you simply found the right equation. Mathematics, to Harold, was the key that unlocked all mysteries. His mother, Karen, approached the world from an entirely different direction. She was an artist and writer who filled their home with vibrant colors, evocative poetry, and questions that had no definitive answers. She perceived patterns in brushstrokes the same way Harold perceived them in data sets and equations. From his parents, Max inherited both mathematical precision and artistic wonder. Dinner conversations in the Tegmark household could veer unpredictably from abstract mathematical proofs to wide-ranging philosophical debates about the nature of reality itself. Sitting between his parents, listening to their exchanges, Max learned to see equations not as dry formulas on paper, but as living shapes, almost like works of art suspended in an invisible space. He was the kind of child who would stay awake late into the night, sketching geometric patterns by lamplight, while other children his age were playing video games or watching television. Numbers fascinated Max, but not because they provided simple answers to well-defined problems. They fascinated him because they seemed to hint at hidden symmetries, at whispers of a grand design running through everything that exists. To young Max, mathematics didn't merely describe the universe from the outside, like a painter capturing a landscape on canvas. Instead, mathematics seemed to pulse through reality itself, like a secret language waiting to be fully decoded and understood. Quietly, almost afraid to speak it aloud, he carried a question that felt too daring, too radical to share with teachers or classmates. What if mathematics wasn't just a tool humans had invented to measure and describe the universe? What if mathematics was the universe itself? That thought became his compass, the North Star that quietly guided every choice he made. In school, while his classmates raced through equations just to get the right answers and move on to the next problem, Max lingered over the beauty behind the mathematics. His teachers often called him a dreamer, brilliant but distracted, someone whose mind seemed to wander into territories beyond the curriculum. But Max wasn't distracted. He was searching. He wasn't content with knowing how mathematics worked. He wanted to know why it worked so perfectly, so universally. Why the same mathematical patterns appeared in contexts as different as quantum mechanics and galactic rotation curves. When others looked at algebra, Max saw structure, an invisible architecture that seemed to shape everything around him, from the arrangement of petals on a flower to the distribution of galaxies across the cosmic web. By the time he reached university in Stockholm, that childhood obsession had crystallized into a quiet but firm conviction. Reality itself, at its deepest level, might be fundamentally mathematical. His papers began to draw attention in academic circles, not for being flashy or making outrageous claims, but for the way they merged rigorous, logical reasoning with profoundly unsettling questions about existence. Eventually, that curiosity pulled him across the Atlantic Ocean to the Massachusetts Institute of Technology, where the language of the universe was spoken fluently in chalk dust and late-night debates among brilliant minds from around the world. In America, Max found himself surrounded by physicists, chasing the deepest mysteries the cosmos had to offer: the Big Bang, quantum mechanics, the ultimate fate of the universe. But while other physicists tried to reconcile the equations of general relativity with quantum theory, patching together frameworks that might unite these two pillars of modern physics, Max kept returning to his childhood question. Maybe the universe doesn't just follow mathematical rules. Maybe the universe is mathematics. From that seed grew one of the boldest ideas in modern science. Max Tegmark didn't just propose a new twist on our understanding of reality. He constructed an entire framework consisting of 4 distinct levels of multiverse, each more radical and mind-bending than the last. But before Tegmark could argue for an infinite reality containing multiple types of universes, the true scale of our own universe had to be revealed piece by piece. That story of discovery began not in a Swedish town or at MIT, but in California in the year 1929. On the summit of Mount Wilson, perched high above the haze and artificial lights of Los Angeles, astronomer Edwin Hubble leaned into the eyepiece of the Hooker telescope. At that moment in history, this was the most powerful telescope on Earth, a 100-inch giant constructed from steel and glass, capable of capturing light from objects more distant than any previous instrument. For years, astronomers had argued passionately about the nature of certain faint, cloudy smudges scattered across the night sky. These ghostly patches were barely visible through smaller telescopes, appearing as fuzzy spirals or elliptical blurs. Some astronomers believed these nebulae, as they were called, were clusters of newborn stars or swirling clouds of gas forming within our own galaxy, the Milky Way. Others suspected something far more extraordinary. These nebulae might be entire galaxies existing far beyond the Milky Way, each one containing billions of stars, comparable to our own sun. This fundamental disagreement about the scale of existence had reached its dramatic peak in 1920 during what became known as the Great Debate, held at the Smithsonian's National Museum of Natural History in Washington, D.C. This wasn't merely a scientific argument about astronomical observations. It was a philosophical battle over the scale of existence itself, over humanity's place in the cosmic order. On one side of this debate stood Harlow Shapley, an ambitious young astronomer from Harvard College Observatory. Shapley had spent years painstakingly mapping the distribution of globular clusters, those dense swarms of ancient stars that orbit galaxies like artificial satellites circling Earth. By carefully studying their brightness and calculating their distances using various astronomical techniques, Shapley had concluded that the Milky Way was far larger than anyone had previously imagined, stretching over 300,000 light-years across. To Shapley, this enormous scale left absolutely no room for other galaxies to exist beyond our own. Those faint smudges in the sky, he insisted with confidence, had to be small nebulae residing within our galactic system. The universe, in his conception, was vast but ultimately self-contained, and Earth occupied a position somewhere far from its center, a revelation that dramatically humbled humanity's cosmic significance. Standing on the opposite side of this intellectual battleground was Heber Curtis, an astronomer from Lick Observatory in California. Curtis possessed a keen eye for photographic detail and believed the night sky held secrets far more profound than Shapley acknowledged. Curtis had carefully studied novae, those sudden stellar explosions that occasionally flare up within spiral nebulae. And he noticed something crucial. These novae appeared much dimmer than comparable novae observed within our galaxy. The only logical explanation, Curtis argued persuasively, was distance. Those spiral nebulae weren't nestled inside the Milky Way. They were located far beyond it, each one constituting a separate island universe containing billions of individual stars. But neither side in this great debate could offer conclusive proof for their position. The technology simply didn't exist yet to measure those vast cosmic distances with sufficient accuracy. So, the fundamental question remained unresolved, suspended between two radically different possibilities. Was the Milky Way the grand total of creation, or merely one insignificant speck floating in an endless cosmic sea? The answer, as history would reveal, came from Edwin Hubble himself, a former lawyer who had turned to astronomy and now worked at the Mount Wilson Observatory. Unlike many of his contemporaries who stumbled onto discoveries by accident, Hubble deliberately set out to solve this problem. He knew about the Great Debate and understood the stakes involved. He wanted hard, irrefutable evidence that would definitively settle the question of whether spiral nebulae were part of our galaxy or separate galaxies entirely. For that crucial task, he needed better data, the kind of precise measurements that only the Hooker telescope, then the largest and most powerful in the world, could provide. Hubble's primary weapon in this quest was a particular type of star called a Cepheid variable. These remarkable stars pulse in brightness at regular, predictable intervals, and astronomers had discovered that the rhythm of these pulsations could reveal the star's true intrinsic brightness. By comparing how bright a Cepheid truly was with how dim it appeared when viewed from Earth, astronomers could calculate its distance using a straightforward geometric relationship. This method had been pioneered by Henrietta Swan Leavitt at Harvard College Observatory in 1912, and her discovery effectively turned Cepheid variables into cosmic measuring sticks, allowing astronomers to gauge distances across previously unimaginable expanses of space. Hubble used these cosmic mile markers to measure the distance to one of the most famous fuzzy smudges in the sky, the Andromeda Nebula. Night after night, month after month, he photographed Andromeda on glass photographic plates, carefully marking faint points of light that changed in brightness over time. Then one evening in October 1923, he scrawled 3 letters on one of his photographic plates, VAR, short for variable star. That tiny note, those 3 hastily written letters, would fundamentally rewrite humanity's understanding of the universe. The distance measurements based on this Cepheid variable demonstrated conclusively that Andromeda wasn't a small cloud of gas within the Milky Way. It was an entire galaxy, located approximately 2.5 million light-years away, existing far beyond the boundaries of our own galactic home. Suddenly, Heber Curtis's island universes were real, confirmed by observational evidence. The scale of existence exploded overnight in human consciousness. What had once appeared to be a single grand metropolis of stars was now revealed to be merely part of a vast cosmic archipelago, with each galaxy containing billions of individual suns scattered across unfathomable distances. Newspapers of the era called Hubble's discovery the greatest breakthrough in astronomy since Copernicus displaced Earth from the center of the solar system. Edwin Hubble became, somewhat reluctantly, a scientific celebrity whose face appeared in popular magazines and whose opinions were sought on matters far beyond his expertise. But to Hubble himself, the real thrill wasn't fame or public recognition. It was the profound realization that the universe appeared to have no obvious boundary, no clear edge beyond which nothing existed. The cosmos seemed to stretch on indefinitely, far beyond what human eyes could perceive, even with the most powerful telescopes. And Edwin Hubble didn't stop with that earth-shattering discovery. Using the same powerful telescope on Mount Wilson, he began a new program of research, measuring what astronomers call redshifts. This phenomenon involves the stretching of light toward longer wavelengths as galaxies move away from us, similar to how the pitch of a siren drops as an ambulance speeds past. To Hubble's considerable surprise, he detected a clear pattern in these measurements. The farther away a galaxy was located, the faster it appeared to be receding from Earth. This relationship, published in 1929, became known as Hubble's law, and it carried a revolutionary implication. The universe wasn't static or unchanging. It was expanding. Space itself was stretching like a vast piece of elastic fabric, carrying galaxies apart from one another like raisins scattered through rising bread dough. The shockwaves from this finding rippled through the entire scientific community and reached all the way to Albert Einstein, the greatest physicist of the age. Einstein had earlier inserted a term he called the cosmological constant into his field equations of general relativity, specifically to keep the universe stable and unchanging, because he, like most scientists of his era, assumed the cosmos must be eternal and static. When Hubble's data arrived, demonstrating beyond doubt that the universe was expanding, Einstein made a pilgrimage to Mount Wilson to look through the Hooker telescope himself and see the evidence firsthand. Looking through the eyepiece at those distant receding galaxies, Einstein reportedly murmured with a mixture of wonder and resignation, "I now see the necessity of a beginning." Later, in conversations with colleagues, he would famously call his assumption of a static universe the greatest blunder of my career. The message delivered by Hubble's observations was crystal clear and profoundly unsettling to the established scientific worldview. The universe was incomprehensibly vast beyond human measure, and it was still growing larger with each passing moment. Think of it like dots painted on the surface of a balloon. As you inflate the balloon, every dot drifts away from every other dot, not because the dots themselves are moving across the balloon's surface, but because the surface itself is expanding. In the same way, galaxies aren't racing through space like rockets. Space itself is stretching between them, carrying them apart. There was no privileged center to this expansion, and no edge where the universe suddenly stopped. There was only endless, accelerating expansion in all directions, simultaneously. Suddenly, the cosmos had acquired something it had never possessed in previous scientific thinking: a history. If everything was currently moving apart, spreading outward in all directions, then logic demanded that at some earlier moment in time, everything must have been closer together. Trace that expansion backward far enough, and you arrive at a moment when all matter, all energy, and even space and time themselves were compressed into an unimaginably hot, dense state. That primordial moment of cosmic birth became known as the Big Bang, the instant when the entire universe burst explosively into being from conditions of almost infinite temperature and density. But for several decades following Hubble's discovery, this idea of a cosmic beginning split the scientific world into opposing camps. Many astronomers and physicists found it philosophically difficult, perhaps even impossible, to accept that everything space, time, matter, and energy could emerge from nothing, that there could be a moment before which nothing existed. The very concept seemed to violate basic intuitions about causation and existence. Something couldn't come from nothing, could it? How could time itself have a beginning? What came before the beginning? Some scientists clung stubbornly to an alternative vision called the steady-state theory, first formally proposed in 1948 by three British scientists, Fred Hoyle, Herman Bondi, and Thomas Gold. These theorists argued that as the universe expanded, creating ever more space between galaxies, new matter continuously formed spontaneously to fill the growing gaps, maintaining the cosmos at a constant average density. The universe, according to their model, had no beginning and would have no end. It simply existed, eternal and essentially unchanging on the largest scales. Despite the local expansion that Hubble had observed, old galaxies might fade and disappear over cosmic timescales, but new ones would continuously form from the spontaneously appearing matter, maintaining the universe in a perpetual steady state. The Big Bang proponents saw things from a radically different perspective. To them, the outward rush of galaxies that Hubble had documented clearly suggested a past explosion, a moment of origin when everything began. They believed the universe had a definite age, a specific birthday that could, in principle, be calculated. But while the mathematics of general relativity and Hubble's observations of an expanding universe pointed strongly towards such a beginning, the evidence remained largely circumstantial throughout the 1,930 seconds, 40 seconds, and 50 seconds. There was no smoking gun, no definitive trace of that first primordial fire that could prove beyond doubt that the Big Bang had actually happened. For nearly 2 decades, both camps fought vigorously for dominance in scientific circles, trading research papers, engaging in heated debates at conferences, giving radio broadcasts, and occasionally even exchanging personal insults. The tension between these worldviews shaped cosmology throughout the mid-20th century. Ironically, the term Big Bang itself was coined mockingly by Fred Hoyle during a BBC radio broadcast in 1949. Hoyle, one of the theory's most vocal critics, never intended the phrase as a compliment or neutral description. He meant it as a dismissive, slightly ridiculous label for an idea he found absurd. Yet the name stuck, and it became the standard terminology for the theory Hoyle despised. By the early 1960 seconds, this fundamental question about the universe's origin was reaching a critical breaking point. Cosmology had transformed into a quiet but intense battleground of competing ideas. With reputations and entire research programs hanging in the balance, the race to find definitive proof was accelerating, with observational astronomers and theoretical physicists working furiously to gather data that might settle the debate once and for all. And then, in one of science's most serendipitous twists, the conclusive evidence appeared from an entirely unexpected direction. Just a few miles apart in New Jersey, 2 groups of scientists were unknowingly closing in on the same world-changing discovery, approaching it from completely different angles. At Bell Telephone Laboratories in Holmdel, 2 young radio engineers named Arno Penzias and Robert Wilson were working on what seemed like a purely technical project. They were fine-tuning a massive horn-shaped microwave antenna that had originally been built for satellite communication experiments. Their immediate goal was straightforward and practical: eliminate all sources of background noise from their extremely sensitive receiver so they could detect the faint signals bouncing off communication satellites. But no matter what they did, regardless of how meticulously they worked, a persistent faint hiss remained in their data. This was a low, steady, crackling static that seemed to come uniformly from every direction in the sky, day and night, summer and winter. The mysterious noise showed no variation whether they pointed the antenna at the sun, at the Milky Way, or at empty regions of space far from any known celestial objects. Penzias and Wilson were nothing if not thorough and meticulous scientists. They systematically checked every electrical connection in their system, recalibrated the entire receiver multiple times, and even climbed inside the horn antenna with cleaning equipment to remove what they diplomatically called white dielectric material, which was, in plain English, pigeon droppings left by birds that had nested inside the antenna. Yet despite all these careful efforts, the mysterious hiss remained absolutely unchanged. It wasn't interference from nearby New York City or from the sun. It wasn't coming from any known source on Earth or any identified celestial object. It was as if the universe itself was whispering to them through their antenna, though they couldn't understand what it was trying to say. The two engineers found themselves in a deeply frustrating situation. They had an excellent instrument. They had eliminated every conventional source of noise they could identify, and yet this stubborn signal persisted, contaminating their data and preventing them from doing the work they had been assigned to do. Meanwhile, just across the Hudson River at Princeton University, physicist Robert Dicke and his research team, including a brilliant young theorist named Jim Peebles, who would decades later win the Nobel Prize for his contributions to cosmology, were working on a very different kind of project. They weren't trying to eliminate noise, they were trying to find it. Specifically, they were attempting to detect the faint afterglow of the Big Bang itself, a remnant heat signature that should still permeate the entire cosmos if the universe had indeed begun in a fireball billions of years ago. Dicke had made a theoretical prediction based on the physics of the early universe. If the cosmos really did begin in an incredibly hot, dense state as the Big Bang theory suggested, then that primordial radiation would have cooled over the subsequent billions of years of cosmic expansion. By now, Dicke calculated, it should have cooled to just a few degrees above absolute zero, the lowest possible temperature. But crucially, it would still be there, spread uniformly across the entire sky in every direction, a faint whisper of creation's first light that had been traveling through space for nearly 14 billion years. Dicke's team was building their own sensitive antenna to search for this cosmic fossil when fate intervened in the form of a telephone call. The two groups didn't initially know about each other's work, operating in their separate spheres of research. But scientific communities are small, and word travels. Penzias and Wilson, increasingly frustrated by their mysterious background noise, mentioned their problem to a colleague who happened to have connections at Princeton. When this astronomer heard their description of a uniform, persistent microwave signal coming from all directions, he immediately recognized what they might have stumbled upon. He contacted Dicke's laboratory to share the news. When word of Penzias and Wilson's mysterious signal reached Princeton, Robert Dicke was in a meeting with his graduate students, excitedly discussing their plans to build an antenna to search for the cosmic microwave background. The phone rang. Dicke answered, listened for a moment, then slowly hung up and turned to his team with a rueful expression. According to witnesses present in the room, he said simply, "Well, boys, we've been scooped." That seemingly frustrating background noise that had plagued Penzias and Wilson for months wasn't a technical glitch or an equipment malfunction. They hadn't been hearing pigeons or electrical interference. What those two Bell Labs engineers had accidentally stumbled upon was nothing less than the cosmic microwave background radiation, the afterglow of creation itself, the ancient light left over from the Big Bang. This radiation represented a fossil imprint from an era when the universe was only about 380,000 years old, long before the first galaxies had formed, before the first stars had ignited, when the cosmos was still a hot, dense soup of matter and energy, beginning its long journey toward the complex structures we see today. It was, in effect, the universe's baby picture, perfectly preserved and spread across the entire sky, waiting patiently for someone with the right instrument to finally detect it. The discovery of the cosmic microwave background was immediately recognized as one of the most important findings in the history of astronomy. It provided the smoking gun evidence that had been missing from the Big Bang theory for decades. The confirmation was definitive. The universe had a beginning. It hadn't existed eternally in a steady state, as Hoyle and his colleagues had argued. Space and time themselves had emerged from an initial moment of creation. The Big Bang theory was no longer just an interesting mathematical possibility or a speculative idea. It was established observational fact, confirmed by direct measurement. Penzias and Wilson would go on to win the Nobel Prize in Physics in 1978 for their accidental discovery, while Dicke's team had to be content with the knowledge that they had predicted the radiation's existence correctly, even if they hadn't been the first to observe it. But when scientists began mapping the cosmic microwave background in greater detail using more sophisticated instruments, they encountered a strange and troubling paradox, an observation that didn't quite fit with the straightforward Big Bang picture. In the late 1980 seconds and early 1990 seconds, satellites like NASA's Cosmic Background Explorer, known by its acronym COBE, began scanning the sky with unprecedented precision, measuring the temperature of this ancient radiation across thousands of different directions. What these satellites discovered was simultaneously beautiful And deeply puzzling, the radiation's temperature was remarkably uniform across the entire sky, measuring almost exactly 2.725 degrees Kelvin everywhere they looked, just a few degrees above absolute zero. No matter which direction the satellite pointed toward distant galaxy clusters or toward the opposite end of the observable universe, the temperature measurements came out nearly identical, differing by less than 1 part in 100,000. This degree of uniformity was astonishing, far more perfect than anyone had anticipated. At first, this extraordinary smoothness seemed poetic, even beautiful in its own way, as if the early universe had been born in a state of perfect balance and harmony. But very quickly, this observation became not just puzzling but deeply confusing to cosmologists who understood its implications. Because if the universe had truly begun in a chaotic hot explosion, basic physics suggested it should have expanded unevenly, leaving behind regions with dramatically different temperatures, depending on local conditions during the expansion. The problem was fundamental. Light, and therefore heat, can only travel at a finite speed, the speed of light, which is fast but not infinite. The observable universe today spans roughly 93 billion light-years from one side to the other, measuring the full diameter of the region from which light has had time to reach us. Yet only about 13.8 billion years have passed since the Big Bang occurred. How can the observable universe be 93 billion light-years across if the universe is only 13.8 billion years old? The answer involves the expansion of space itself, which can carry distant regions apart faster than the speed of light without violating relativity. But here's the critical point. This means that distant regions we can now observe are so far apart that, according to standard Big Bang cosmology, light from one side could never have reached the other side during the early universe. They had never been in contact with each other, never had an opportunity to exchange energy and equalize their temperatures. Put another way, there simply hadn't been enough time for the universe to thermally mix itself. It was as if you had taken 2 cups of water, one boiling hot and one ice cold, placed them at opposite ends of a football field, and forbidden them from any contact whatsoever, and yet, when you measured their temperatures, you found they were identical down to tiny fractions of a degree. Somehow, regions of the cosmos that had never communicated, that had never been close enough to exchange heat and reach thermal equilibrium, had mysteriously agreed on exactly the same temperature. This became known among cosmologists as the horizon problem, and it wasn't a minor technical detail or a small discrepancy that could be ignored. It struck at the very heart of the Big Bang model, threatening to undermine the entire theoretical framework. For those widely separated patches of sky to look so remarkably similar in temperature, they must have once been part of a much smaller, denser region that was capable of equilibrating thermally before being stretched apart by cosmic expansion. But the standard Big Bang theory as it existed in the 1,970 seconds didn't allow for that possibility. The mathematics simply didn't accommodate it. The expansion proceeded smoothly from a hot initial state, but that initial state was already too spread out for different regions to have coordinated their temperatures. Physicists began to fully grasp just how bizarre and troubling this observation really was. Imagine 2 different classrooms separated by vast distance, one in New York City and one in Tokyo, on opposite sides of the planet. The teacher in each classroom gives the students an identical complex assignment and strictly forbids them from communicating with each other in any way. No phone calls, no emails, no messages of any kind. When the homework assignments are collected the next day, every single answer in both classrooms, including the specific mistakes and errors, turns out to be exactly the same, word for word, number for number. That's essentially what scientists were observing in the cosmic microwave background. Enormous regions of space, separated by distances so vast that no signal could possibly have passed between them in the time available, had somehow coordinated their physical properties to produce identical results. They had synchronized their temperatures without any apparent means of communication. Something hidden and unexpected had to connect these distant regions, some event or mechanism operating in the universe's earliest moments that allowed widely separated patches of space to share information and reach equilibrium before being torn apart by subsequent cosmic expansion. Whatever this mechanism was, it had to have operated almost instantaneously after the Big Bang, and it had to have been powerful enough to smooth out and homogenize the entire observable universe before the standard expansion took over. The physics community was confronted with a genuine mystery, a contradiction between theory and observation that demanded an explanation. That's when a young physicist at MIT, working in relative obscurity late one night in December 1979, stumbled upon an idea that would not only solve the horizon problem, but fundamentally rewrite our understanding of the universe's earliest moments and open the door to the concept of multiple universes. Alan Guth was a 32-year-old postdoctoral researcher at that time, struggling to establish himself in the competitive world of theoretical physics. He was not yet a prominent figure in cosmology, not a household name or even particularly well known within his field. He was working on problems related to particle physics and quantum field theory in the early universe, trying to understand how certain exotic particles might have behaved in the extreme conditions immediately following the Big Bang. And then, while working through some calculations late at night, he asked himself a seemingly simple question. What if the universe itself went through an extraordinarily brief burst of faster-than-light expansion in its very first instant of existence? In his research notebook, Guth underlined a phrase that captured his excitement at this realization: spectacular realization. That spark of insight, that single question asked late at night, became the foundation for what is now called the theory of cosmic inflation. According to this revolutionary idea, in an almost incomprehensibly brief moment, less than a trillionth of a second after the Big Bang began, the universe underwent exponential expansion. Space didn't just grow gradually or steadily. It exploded in size at a rate that vastly exceeded the speed of light, ballooning outward and carrying all matter and energy along with it. During this inflationary epoch, the universe expanded by a factor of at least 10 to the power of 26, and possibly much more. To put that in perspective, if you took something the size of an atom and expanded it by that factor, it would become larger than the observable universe we see today. And this all happened in a tiny fraction of a second. Far too brief for human intuition to grasp. After this period of inflation ended, the universe continued expanding, but at the much slower, more sedate rate that Hubble had observed in the 1,920 seconds. Inflation elegantly and simultaneously solved three profound puzzles that had plagued cosmologists for years. First, it explained why the universe appears geometrically flat on large scales rather than curved or chaotic. The explosive expansion stretched any initial curvature so smooth that we can't detect it, like inflating a balloon to enormous size makes its surface appear flat from the perspective of a small observer. Second, and most importantly for our story, inflation solved the horizon problem in one stroke. Before inflation began, the entire region that would eventually become our observable universe was indeed small enough for all its parts to be in thermal contact, allowing temperatures to equalize. Then, inflation stretched this tiny, thermally equilibrated patch to enormous size, creating the uniformity we observe today across the cosmic microwave background. Distant regions look the same because they were once close together before inflation blew them apart. Third, inflation explained why hypothetical particles called magnetic monopoles, which are predicted by certain particle physics theories and should have been produced abundantly in the early universe, are nowhere to be found in nature. They were diluted to undetectable levels by inflation's rapid expansion, spread so thin across the vastly inflated cosmos that we simply never encounter them. Think of it like kneading bread dough that's filled with small air bubbles. When you place that dough in an extremely hot oven, it rises dramatically, and those bubbles stretch and thin out until the bread emerges smooth and uniform. Inflation was the cosmic oven that smoothed the universe into the flat, even structure we observe today. But bold ideas in physics, no matter how elegant or mathematically beautiful, only survive and become established science if nature leaves behind some observable fingerprint, some testable prediction that can be verified or falsified through experiment. Guth's inflation theory made a specific, concrete prediction about such a fingerprint. He predicted that quantum fluctuations in the newborn universe, tiny, random jitters in energy and matter, at the subatomic scale that are an inherent feature of quantum mechanics, would be stretched to cosmic size by inflation's exponential expansion. These microscopic quantum jiggles would be blown up and frozen into the fabric of space-time itself, appearing as subtle ripples, tiny variations in density and temperature that should be detectable in the cosmic microwave background. For several years after Guth proposed inflation, the cosmic microwave background still looked perfectly smooth to observational instruments. The technology simply wasn't sensitive enough to detect these predicted tiny variations. But in 1992, in one of those moments that sends shockwaves through the entire scientific community, NASA's COBE satellite finally detected them. The satellite found minute temperature variations, anisotropies in the cosmic microwave background, differing from place to place by only about 1 part in 100,000, exactly the kind of subtle ripples that inflation had predicted. George Smoot, the astrophysicist who led the COBE team, was so moved by seeing the first images of these primordial fluctuations that he made a famous remark to reporters. "If you're religious, it's like looking at God." These weren't just random spots on a map. They were the seeds of all cosmic structure, the tiny density variations that would eventually grow under gravity's influence to become galaxies, galaxy clusters, and the vast cosmic web of structure we observe throughout the universe today. Everything that exists, every star, every planet, every living creature ultimately traces its existence back to these quantum fluctuations in the first fraction of a second after creation. Later, space missions refined these measurements with ever-increasing precision. The Wilkinson Microwave Anisotropy Probe, known as WMAP, operated throughout the 2000s, and the European Space Agency's Planck satellite conducted even more detailed surveys in the 2010 seconds. These missions revealed a universe that was astonishingly flat according to the measurements, confirming inflation's predictions, and seeded with precisely the kind of Gaussian ripples random fluctuations following a specific statistical pattern that inflation had forecast decades earlier. The match between theory and observation was so precise, so detailed, that inflation moved from being a speculative idea to being the leading framework for understanding the universe's first moments. But here's where the implications became truly staggering, where the story takes a turn from understanding our universe to contemplating something far more vast and unsettling. If inflation could stretch our observable patch of the universe so dramatically, what about the regions beyond what we can see? The mathematics of inflation suggested something profound. The cosmos might not just be vast or impressively large. It might be genuinely infinite, extending forever in all directions without any boundary or edge. Max Tegmark watched all of these discoveries unfold from his position at MIT, surrounded by colleagues who were working on the detailed mathematics of cosmic inflation and analyzing data from satellite observations. He filled chalkboards with equations, tracing the story of the cosmos in chalk dust and mathematical symbols. Tegmark observed how the discoveries seemed to stack like chapters in a single epic narrative, each one building on what came before to reveal an ever more magnificent and humbling picture of existence. First had come Edwin Hubble in the 1,920 seconds, whose observations through the Mount Wilson telescope revealed that the Milky Way galaxy was not the entire universe, as previously believed, but merely one island among billions of galaxies scattered across an almost unimaginable cosmic expanse. That fundamental discovery expanded humanity's view of space itself, pushing the boundaries of the known universe outward by factors of millions. But Hubble's discovery also raised profound new questions. If the universe contained all these galaxies, and if they were all rushing away from each other, how had it all begun? What was the origin of this vast cosmic architecture? Then came Penzias and Wilson in 1965, who offered a crucial clue with their accidental discovery of the cosmic microwave background. This faint afterglow represented leftover heat from the universe's fiery birth, tangible physical evidence preserved across the sky. Suddenly, the universe wasn't eternal and unchanging. It had a definite beginning, a birthday that could be calculated, a moment of creation whose remnant glow we could still detect billions of years later. The cosmos had transformed from something eternal and static into something with a history, a narrative arc from hot, dense beginnings to the cool, structured present. Yet this newborn cosmos held deep mysteries that the simple Big Bang picture couldn't explain. How could regions of space that had never been in contact share identical temperatures? Why was the universe so geometrically flat? These puzzles demanded explanation. Alan Guth provided that explanation in 1981 by proposing that the universe underwent a mind-boggling period of exponential inflation in its first fraction of a second. Guth's insight connected those widely separated regions that appeared to have no way to communicate they had been close together before inflation explosively separated them, allowing them to coordinate their properties before being blown apart to cosmic distances. Satellites like COBE, WMAP, and Planck subsequently mapped the faint ripples in the cosmic microwave background with exquisite precision, confirming inflation's predictions in stunning detail. The universe these instruments revealed was not tangled or chaotically curved, but remarkably flat, stretching outward with no detectable curvature, seemingly extending forever. Each discovery naturally flowed into the next, creating a coherent narrative. Hubble revealed the true scale of space. Penzias and Wilson revealed a cosmic origin. Guth explained the universe's structure and uniformity, and the satellites confirmed these theoretical predictions with hard observational data. As Max Tegmark studied these developments from his position at MIT, absorbing the implications of inflation theory and flat geometry, a startling possibility emerged from the mathematics, something that most cosmologists hadn't fully appreciated yet. If the universe was spatially flat and infinite, stretching on forever without curving back on itself, then a profound and unsettling conclusion followed almost inevitably. What we can observe from Earth, that region of space from which light has had time to reach us in the 13.8 billion years since the Big Bang, represents only an infinitesimally tiny patch of something far more vast, possibly something truly infinite. From behind his MIT chalkboard, surrounded by equations describing cosmic geometry and quantum mechanics, Tegmark noticed a profound mathematical implication hidden within these numbers, something that emerged naturally from combining quantum mechanics with infinite space. Within our observable universe alone, the number of possible ways that atoms and particles could be arranged is staggeringly large but ultimately finite. Physicists have calculated this number to be approximately 10 raised to the power of 118, a 1 followed by 118 zeros. That's an almost incomprehensibly huge number, far exceeding the number of atoms in the observable universe, far exceeding anything human minds can intuitively grasp. But here's the crucial insight. In an infinite cosmos, that unimaginably large but finite number suddenly becomes tiny, essentially insignificant. If space truly extends forever in all directions, then every possible arrangement of matter, every possible configuration of atoms, every possible sequence of events must eventually repeat somewhere out there in the vast infinite expanse. It's not just possible or probable, it's mathematically inevitable. Somewhere out in that endless sea of space, far beyond the cosmic horizon where our telescopes can never reach, there must exist another patch of the universe that mirrors our own down to the last atom, down to the smallest possible detail. Somewhere in the infinite cosmos, there's another Earth orbiting another sun, with another version of you reading these exact words at this exact moment. The mathematics doesn't just allow for this possibility, it guarantees it. This realization is both thrilling and deeply unsettling. It means that somewhere among those countless regions of space, an exact copy of this universe exists, a silent twin, living out an identical history among infinite possibilities. Tegmark enjoyed making this mind-bending concept accessible to general audiences through simple, everyday analogies. He often used socks to explain the idea, turning profound cosmic implications into something anyone could understand. Imagine you wake up tomorrow morning and reach for a pair of blue socks from your drawer, just as you do every morning without much thought. It's such an ordinary, mundane action that you barely register making the choice. Now, imagine traveling to another region of the infinite universe, impossibly far beyond what any telescope could ever observe, beyond the cosmic horizon where light from those distant regions hasn't had time to reach us yet. In that distant patch of space, there's another version of you, living on another Earth that formed around another sun. This other you is going through the same morning routine at the corresponding moment in their life, but with a tiny difference. This time, that version of you reaches for red socks instead of blue. That's the only variation in an otherwise identical life. Travel even farther out into the infinite cosmos, to yet another region unimaginably distant from both the first two, and you'll find a version of you who made yet another choice. Perhaps this version never bought socks at all, preferring to go barefoot or choosing some entirely different morning routine. And if you could somehow travel to still more distant regions, eventually, you'd encounter a version of you who is living exactly the same life you're living right now, making precisely the same choices, wearing exactly the same blue socks, having exactly the same thoughts at exactly the same moments, completely unaware that multiple versions of you exist, scattered across the infinite landscape of space, like cosmic twins, separated by distances that make intergalactic space seem tiny by comparison. Every small choice you make throughout your life, every tiny variation in circumstance, every minor difference in outcome happens somewhere in this endless, infinite cosmos. It's not science fiction or wishful thinking. It's a direct mathematical consequence of combining quantum mechanics with infinite space. That's the strange and inescapable rule of infinity, operating on a cosmic scale. Infinity doesn't merely allow possibilities to occur somewhere. It absolutely guarantees that they will occur. And not just once, but infinitely many times across the boundless expanse of space. Think of it like rolling a pair of dice over and over forever, never stopping. Every possible combination of numbers, double sixes, double ones, every conceivable sequence will eventually appear. In fact, each combination will appear infinitely many times if you keep rolling forever. There's no escape from this mathematical certainty. Now scale that simple dice analogy up to encompass the entire universe. Every possible arrangement of atoms, every choice you've ever made or could ever make, every variation of Earth's history, every possible configuration of stars and planets will repeat somewhere in that infinite space. Not just once, but infinitely many times, scattered across distances so vast they defy human comprehension. And within that endless repetition, Max Tegmark glimpsed something even more profound than mere copies of our universe endlessly repeating. Infinity didn't just mechanically create duplicates of our world scattered across unimaginable distances. The mathematics hinted at something deeper and more fundamental, a layered structure to reality itself, with level upon level stretching beyond anything we could easily imagine or directly observe. Our repeated universes were perhaps just the beginning, the first and simplest layer in a far more complex hierarchy of existence. In 2003, Tegmark decided to lay out all of these ideas for the general public in an article published in Scientific American, one of the most respected popular science magazines in the world. The article opened with a deliberately provocative statement designed to capture readers' attention. Somewhere out there in the infinite cosmos, there's a copy of you that differs only by something as trivial as the color of your socks. Tegmark knew some readers would dismiss this as absurd, as the kind of speculation that belonged in science fiction rather than scientific journals. But he also knew the mathematics supported this conclusion rigorously. He wrote, "Don't underestimate the implications of what might seem like a simple joke about socks. Beneath that seemingly trivial example lay a radical truth about the nature of existence itself. Cosmology's long march from discovering distant galaxies to understanding the Big Bang to developing inflation theory had inadvertently built a ladder that led straight into the multiverse concept. Each discovery, each refinement of theory, each new observation had added another rung to this ladder. And now that ladder reached into truly strange territory. Tegmark's first rung on that ladder ascending into the multiverse was what he systematically called the Level 1 multiverse. This was, in some sense, the most conservative and least exotic type of multiverse, emerging directly and naturally from well-established physics without requiring any speculative new theories or unproven assumptions. The Level 1 multiverse simply took seriously the implications of an infinite, flat universe produced by cosmic inflation. To understand this concept clearly, imagine you flip a coin 100 times in succession. In our particular observable region of the universe, you might get a specific sequence: heads, tails, heads, heads, tails, and so on through all 100 flips, producing one particular pattern out of the vast number of possible sequences. But in an infinite universe extending forever beyond our cosmic horizon, every conceivable sequence of 100 coin flips exists somewhere. That means there's a region of space unimaginably far away and forever beyond our ability to observe, where the sequence came out as 100 consecutive heads. And there's another distant region where the sequence perfectly matched your exact flips, and infinitely many other regions with every other possible combination. Now, scale this coin-flipping analogy up dramatically to encompass entire planets and civilizations. In our observable patch of the universe, our specific region of the cosmos bounded by the distance light has traveled since the Big Bang. You are sitting somewhere right now, reading or listening to this explanation. But far beyond the observable horizon, in regions of space so distant that light from them hasn't yet had time to reach us, and never will, due to the accelerating expansion of the universe, there exists another region where the same fundamental laws of physics apply without any change. Gravity works the same way, atoms behave identically, chemistry follows the same rules. But the initial conditions immediately following the Big Bang were slightly different in that distant region compared to ours. In one of those distant regions, separated from us by distances measured not in light years, but in trillions of light years or more. There's an Earth almost identical to ours, with a person almost identical to you in every conceivable way. The only difference might be something utterly trivial. Perhaps this other you is reading or hearing this explanation in Spanish instead of English. Or perhaps they paused to get a glass of water while you continued without interruption. These infinitesimal variations play out endlessly across infinite space. In another vastly distant region, there's an Earth where the cosmic dice rolled differently during the planet's formation and evolutionary history. Perhaps the asteroid that killed the dinosaurs 65 million years ago missed Earth entirely in that region. In that alternative Earth, dinosaurs never went extinct, mammals never rose to dominance, and human beings never evolved at all. Instead, that planet might be inhabited by intelligent descendants of velociraptors or some other dinosaur lineage, living out their own history under their own alien sun, completely unaware that countless other Earths exist in distant patches of the infinite cosmos. This is the essence of Max Tegmark's Level 1 multiverse. Infinite space means infinite variety, and infinite variety means everything that can happen does happen somewhere. Infinity doesn't merely suggest the existence of these duplicate and variant regions. The mathematics guarantees their existence as surely as the laws of probability guarantee that any specific combination will eventually appear if you keep rolling dice forever. These other regions aren't separate universes in the sense of being disconnected from our spacetime. They're part of the same continuous spatial fabric, the same single universe, just located so far away that we can never observe them, never interact with them, never confirm their existence through direct measurement. The Level 1 multiverse doesn't depend on exotic physics, untested theories, or speculative mathematics. It emerges straightforwardly from ideas that are well established in modern cosmology. The concept of an infinite cosmos stretched flat by cosmic inflation. It represents the simplest possible doorway into multiverse thinking, requiring no leap beyond known and tested science, demanding only the intellectual courage to accept the full implications of infinity itself. If space goes on forever, and if the laws of physics operate uniformly throughout that space, then repetition is inevitable. Everything that can exist does exist, infinitely many times over. But for Max Tegmark, infinity of this kind wasn't an endpoint or final destination in understanding reality. It was merely an opening move, the first step in a much longer journey into stranger territories. If the sheer spatial extent of the universe could spawn endless copies of us simply by stretching far enough, what else might the laws of physics permit? And perhaps more unsettling, why should the fundamental rules governing reality remain fixed and unchanging across all of existence? What if even the laws of physics themselves could vary from one region to another? Tegmark couldn't leave these questions alone. They gnawed at him, the way the horizon problem had gnawed at Alan Guth before the invention of inflation. From the relatively calm and comprehensible infinity of Level 1, where familiar physics simply repeated endlessly across space, Tegmark's mind turned toward considerably stranger possibilities that emerged from other areas of theoretical physics. And it is here, at this juncture in our story, that we shift from the gentle, almost comforting infinity of spatial repetition to something far more radical and conceptually challenging the idea that different regions of existence might operate under fundamentally different physical laws. To understand where these ideas came from, we need to leave MIT temporarily and travel backward in time, eastward across the Atlantic Ocean to Moscow in the year 1948. The city was gray with ideological conformity and cold with political control. Joseph Stalin's portrait hung prominently over every classroom, every public building, every space where citizens gathered. Scientific inquiry in the Soviet Union wasn't a free search for truth wherever it might lead. Science was a servant of the state, expected to conform to Marxist-Leninist ideology and support the political system's fundamental assumptions. The universe, according to official Soviet doctrine, was eternal, stable, perfectly knowable, and entirely consistent with materialist philosophy, just as Karl Marx had envisioned in his writings. There could be no moment of creation, no cosmic beginning, no Big Bang. Such ideas smacked too much of religious thinking about creation ex nihilo, about a divine creator bringing the universe into being. The cosmos itself, Soviet authorities insisted, had to obey the dialectical materialist philosophy of the Communist Party. Any suggestion otherwise was politically suspect, potentially dangerous to one's career or even personal safety. But Andrei Linde was not the kind of boy who fit comfortably inside that ideological box. From early childhood, he was the sort of student who asked too many questions, who filled the margins of his school notebooks with symbols and equations that didn't belong to any assigned lesson. His teachers wanted tidy, approved answers that conformed to official doctrine. Young Andrei wanted to explore the unknown, to question assumptions, to follow ideas wherever they led, regardless of whether they fit comfortably within party-approved frameworks. Late at night, while Moscow slept under winter darkness and most citizens were engaged in the simple struggle for daily survival in a difficult society, Andrei read everything he could find, often consuming materials that had been smuggled into the country. These were copies of Western scientific journals passed secretly from hand to hand like contraband, like forbidden literature that might get someone in serious trouble if discovered by authorities. Those clandestinely shared pages spoke of galaxies existing far beyond the Milky Way, of light emanating from the universe's beginning, of ideas and discoveries his official Soviet textbooks pretended didn't exist or dismissed as Western bourgeois pseudoscience. To young Linde, these forbidden papers weren't just interesting scientific findings. They represented glimpses of intellectual freedom, proof that reality was far larger and stranger than the narrow borders drawn around him by political ideology. They showed that the universe didn't care about human politics or ideological systems. Nature followed its own rules, indifferent to what any political party wanted to believe. By the 1970 seconds, Andrei Linde had successfully navigated the complex and often treacherous path through Soviet academia to reach the heart of scientific research at Moscow State University. The institution itself was a paradox wrapped in contradictions. It housed some of the most brilliant minds in the Soviet Union, physicists and mathematicians of extraordinary talent, yet all of them were trapped within a system that fundamentally distrusted intellectual curiosity and independent thinking. Lecture halls were filled with chalk dust and cautious ambition, where brilliant ideas had to be expressed carefully, with every word measured for potential political implications. The professors spoke with deliberate care, always aware that someone might be listening, always conscious that a carelessly phrased idea could be interpreted as ideological deviation. But between the carefully chosen words, beneath the surface of official conformity, a quiet rebellion stirred among the younger generation of physicists. Linde found himself among other restless young scientists who wanted more than the official doctrine would allow, who hungered for real answers about the cosmos, regardless of whether those answers fit comfortably within Marxist-Leninist philosophy. In whispered conversations conducted over weak tea in cramped apartments, these young physicists traded rumors and fragmentary information about discoveries happening in the West, in the capitalist countries that official propaganda portrayed as decadent and scientifically backward. They heard about Hubble's observations showing galaxies racing away from each other through expanding space, definitive proof that the universe itself was stretching, growing larger with each passing moment. This directly contradicted the official Soviet position of an eternal, unchanging cosmos. Then came the electrifying story from 1965, when two American engineers working in New Jersey, Arno Penzias and Robert Wilson, had accidentally detected a mysterious hiss coming from every direction in the sky. This wasn't random noise or equipment malfunction. It was the leftover heat from creation itself, the cosmic microwave background radiation preserving a fossil record of the universe's fiery birth. The evidence had become undeniable, at least to scientists willing to look at it honestly and follow the data where it led. The universe had not always existed. It had a definite beginning, a moment of creation that no Soviet textbook was permitted to acknowledge or discuss openly. Then in 1981, news from across the Iron Curtain filtered its way into Moscow's underground scientific circles, traveling through informal networks of researchers who maintained contacts in the West despite official restrictions. Alan Guth, a young and relatively unknown physicist working at MIT in America, had published a revolutionary paper proposing something audaciously bold: cosmic inflation. According to Guth's mathematical framework, which Linde and his colleagues studied with intense interest whenever they could obtain copies of Western journals, the universe had undergone a period of exponential expansion in its first inconceivably brief instant of existence. In that first moment after the Big Bang, lasting for approximately 10 to the minus 32 seconds a decimal point, followed by 31 zeros and then a 1, an interval of time so brief that human language lacks adequate words to describe it. Space had ballooned outward, faster than the speed of light itself. That single burst of exponential growth, Guth argued, could elegantly explain several otherwise puzzling features of our cosmos that had long troubled cosmologists. It explained why the universe looked so remarkably smooth and uniform when examined on the largest scales. It explained why space appeared geometrically flat rather than curved. And it explained why distant, apparently disconnected regions of the cosmos shared identical temperatures despite having no apparent means of communication. For Andrei Linde, reading Guth's work was simultaneously thrilling and deeply frustrating. The basic concept was brilliant, elegant in its mathematical structure, revolutionary in its implications. But when Linde worked carefully through the details of Guth's original model, calculating the consequences step by step, he discovered what he considered to be a fatal flaw in the implementation. According to Guth's mathematics, inflation ended too abruptly everywhere at once in a coordinated fashion. This sudden, simultaneous ending would have left the universe scarred with certain types of defects, dense concentrations, and knots of energy predicted by quantum field theory that simply don't exist in the sky we actually observe through telescopes. It was like reading a brilliant novel that stumbled badly in its final chapter, or hearing a beautiful symphony that ended with a jarring, discordant note that ruined the overall composition. The core insight seemed correct and profound, but the mathematical details needed refinement. The theory required a smoother, more physically realistic ending to match observational reality, and Linde found he couldn't stop thinking about how to fix this problem, how to preserve inflation's explanatory power while eliminating its problematic consequences. The flaw in Guth's model gnawed at Linde's mind like a persistent itch he couldn't scratch, like a loose thread in a tapestry that he couldn't stop pulling. Night after night, Linde remained in his small Moscow apartment, working by the dim light of a single lamp, while the city outside his window gradually fell silent. Papers covered every available surface of his small desk, filled with equations, crossed-out calculations, and new attempts to resolve the mathematical difficulties. He systematically ran through every possibility he could imagine, searching methodically for a version of inflation that could preserve all the theory's successful predictions while fixing the broken ending that left unobserved defects in its wake. And then one night, after months of sustained effort, a new thought began to crystallize in his mind, emerging gradually from the fog of equations and calculations. What if inflation didn't have to stop everywhere at once in a coordinated, synchronized fashion? What if, instead of ending simultaneously throughout space, like a light switch being flipped off everywhere at the same moment, it ended in scattered patches, in isolated regions, like water boiling where some bubbles burst and stop growing while others continue expanding, each following its own independent timeline? The idea refused to leave him once it had lodged itself in his consciousness. He followed it wherever it led, testing it against the mathematics, pushing it further to explore its full implications. Slowly, painstakingly, the picture came into sharper focus, the details filling in like a photograph gradually developing in a chemical bath. By 1983, after years of persistent work conducted in the intellectually stifling environment of Soviet academia, Linde achieved his breakthrough. It wasn't a matter of sudden inspiration or a flash of mystical insight striking from nowhere. It was the result of sustained, disciplined effort, of refusing to give up when the problem seemed intractable. He called his refined version of the theory chaotic inflation, and it represented a fundamental advance beyond Guth's original pioneering work. Guth had lit the first spark of the inflation idea, demonstrating that rapid exponential expansion could solve otherwise intractable cosmological problems. But Linde transformed that spark into what he would later describe as a firestorm, taking the concept in directions Guth had never imagined. Inflation, Linde realized through his detailed calculations, wasn't necessarily a one-time event that came and went in the universe's first moment. Under the right conditions, which his equations suggested were quite natural and generic, it could continue happening eternally across different regions of space, never truly stopping everywhere. Some pockets of space would cool down and exit the inflationary phase, forming stable regions where normal physics could operate, and structures like galaxies could eventually form. These would become universes like ours, governed by familiar physical laws, but other regions would continue expanding exponentially, endlessly creating new space, eternally generating new pockets that would eventually cool and form their own stable regions. Inflation in Linde's refined picture didn't end uniformly. It multiplied, branched, propagated itself eternally across an ever-growing volume of space-time. Think of the universe not as a single firework exploding once and then fading away, but as a boundless ocean of quantum energy fields. In this infinite ocean, bubbles constantly form in different locations as quantum fluctuations cause inflation to slow down and stop in isolated regions. Each bubble represents a universe, a region of space where inflation has ended and normal physical processes can operate. Each bubble is effectively sealed off from its neighbors, separated and pushed apart by the relentless exponential growth of space itself between them, making it impossible for inhabitants of one bubble to ever observe or visit neighboring bubbles. Inside each bubble, as the energy driving inflation finally dissipates and converts into ordinary matter and radiation, the fundamental rules of physical reality lock into place. The constants of nature, the strength of gravity, the mass of the electron, the speed of light, the strength of nuclear forces, all crystallize and become fixed. And here's the truly revolutionary leap that Linde made. Those constants, those fundamental parameters that determine how physics operates, didn't necessarily have to be the same in every bubble. Different bubbles might have different values for these fundamental constants, making them radically different universes with alien physics. One bubble might have gravity that's substantially stronger than in our universe, causing matter to collapse into black holes so readily that stars and galaxies never have a chance to form. Another bubble might have weaker gravity, so weak that matter never clumps together sufficiently to create gravitationally bound structures, leaving only a thin, eternally expanding soup of isolated particles. Still, another bubble might have different values for the fundamental forces governing atomic structure, making stable atoms impossible, or creating entirely different periodic tables of elements with radically alien chemistry. Linde wasn't merely tweaking or refining the Big Bang Theory, making small adjustments to an existing framework. He was proposing something far more radical and philosophically profound. A cosmic landscape consisting of endless bubble universes, each born from eternal inflation, each potentially operating under its own variant rules of physics. In Linde's revolutionary vision, inflation didn't stop everywhere at once like a synchronized global event. It ended locally, here and there, in scattered regions like bubbles forming continuously in an infinite pot of water kept at eternal boiling temperature. Each bubble marked the birth of a new universe, born in its own localized burst of expansion, with its own version of a Big Bang occurring inside when inflation finally ceased in that particular region. Inside one bubble, the specific conditions and parameters might closely resemble ours, leading to familiar physics with galaxies, stars, planets, and perhaps even life. In another bubble, somewhere else in the vast cosmic landscape, gravity could be 10 times stronger or 10 times weaker, making the evolution of that universe utterly different from ours. Some bubbles might collapse back on themselves almost immediately after forming, existing for only a cosmological instant before vanishing. Others might stretch and cool into vast, stable regions capable of supporting complex structures and persisting for trillions of years or more. The implication was staggering. There wasn't just one cosmos anymore, just one universe representing the totality of physical existence. Instead, there was a frothing, eternally churning sea of universes, an infinite ensemble of bubble universes, continuously budding off from an eternally inflating background spacetime. No one could definitively say how many such universes existed in total. The number might be merely enormous, trillions upon trillions, or it might be literally infinite, with new universes being born continuously throughout eternity. Each bubble universe was sealed off from all the others by the vast, exponentially expanding regions between them, making direct observation or communication across bubble boundaries impossible, even in principle. From our perspective, as inhabitants trapped inside one particular bubble, we could never cross that cosmic divide separating us from neighboring universes. We could never see beyond our own bubble's edge, never send signals to other universes, never empirically verify that they exist at all. Yet according to Linde's detailed mathematical analysis, based on well-established principles of quantum field theory and general relativity, the eternal process of universe creation never stopped. Somewhere in the vast cosmic landscape, right at this very moment, new bubble universes are still being born, still emerging from the quantum foam of eternally inflating space-time. For Andrei Linde, who had spent his formative years trapped within the ideological confines of the Soviet Union, this scientific concept carried sharp personal resonance. His own lived experience felt like existing in a closed bubble, sealed off by political borders, censorship, and authoritarian control from the wider world beyond. So when he finally succeeded in emigrating from the Soviet Union to California in the early 1990 seconds, after the USSR's collapse made such moves possible, accepting a faculty position at Stanford University, it felt emotionally like stepping through a membrane into a genuinely different universe. Entirely freer, brighter, more open, buzzing with unrestricted intellectual debate and the free exchange of ideas. His personal biography, in some sense, mirrored his scientific theory. Just as his equations described a multiverse of distinct worlds, each governed by its own set of rules, and each shaped by its own particular beginning conditions, Linde had lived through a transition between two radically different political and intellectual universes. The analogy wasn't perfect, of course, but it gave him a visceral, emotional understanding of what it might mean for reality itself to contain multiple disconnected domains, each with its own character. But Linde's theoretical framework opened a deeper and more philosophically troubling question that would haunt cosmology for decades afterward. If these bubble universes truly existed as his mathematics suggested, were they merely variations of our own universe? Similar to Tegmark's Level 1, repeating worlds where only initial conditions differ while laws remain fixed? Or did they represent something far more radical? Universes following entirely different laws of physics, places where reality itself rewrites its fundamental operating instructions, where the basic constants and forces governing existence take on completely different values? Back in the early 1980 seconds, when Linde first proposed eternal inflation and its bubble universe implications, most mainstream physicists dismissed the idea as too wild, too speculative, too untestable to deserve serious consideration. It sounded more like science fiction or metaphysical speculation than proper physics. How could you possibly test or verify the existence of other universes that were by definition forever beyond the reach of our observations? What did it even mean to claim something existed if no conceivable experiment could ever detect it? But then, quite unexpectedly, a surprising ally for the multiverse concept emerged from an entirely different corner of theoretical physics, from researchers working on problems that seemed completely unrelated to cosmology. In the 1970 seconds, a brilliant young physicist from the Bronx named Leonard Susskind found himself wrestling with one of the deepest and most stubborn puzzles confronting fundamental physics. What if matter at its most basic level wasn't composed of point-like particles as physicists had assumed for decades, but instead consisted of tiny vibrating loops of energy, extended one-dimensional objects rather than zero-dimensional points? That deceptively simple question became the conceptual seed from which string theory grew, ultimately becoming one of the most ambitious and mathematically sophisticated frameworks in all of physics. Each fundamental string, according to this theory, could vibrate in countless different ways, similar to how a violin string can produce different musical notes depending on exactly how it vibrates. And each distinct vibration pattern of a string created different kinds of particles with different properties: electrons, quarks, photons, gravitons, and potentially many other particles. The strings themselves were the fundamental reality, and what we perceive as different particles were merely different vibrational modes of these underlying strings. The mathematics required to make string theory work consistently turned out to be extraordinarily complex and beautiful, requiring the introduction of extra-spatial dimensions beyond the three we experience in everyday life. But the theory held tremendous promise. It offered the tantalizing possibility of unifying quantum mechanics with general relativity, those two great pillars of 20th century physics that had stubbornly resisted integration into a single coherent framework. String theory might provide the long-sought theory of everything that Einstein had dreamed about, a single mathematical structure encompassing all physical phenomena. However, By the early 2000s, as string theorists explored their mathematical framework more deeply, the theory took an unexpected and shocking turn that would fundamentally change how physicists thought about it. Instead of describing one unique, elegant universe with a single set of physical laws, as many had hoped, string theory appeared to allow for roughly 10 to the power of 500 possible vacuum states, different stable configurations the theory could settle into. That number is so monstrously vast that it makes even the number of atoms in the observable universe, estimated at around 10 to the power of 80, seem laughably tiny by comparison. Each of these possible vacuum states came with its own specific physics, its own set of parameters and constants. In some states, gravity might be relatively strong. In others, it could be almost negligibly weak. Space itself might have more or fewer effective dimensions, depending on how extra dimensions curled up and compacted. Time might flow differently, or couple to matter in unfamiliar ways. The fundamental forces electromagnetism, the strong nuclear force, the weak nuclear force might have dramatically different relative strengths, altering how particles interact and how matter behaves at every scale. It was as if the universe wasn't constrained to play one specific song with fixed rules and a predetermined melody. Instead, reality had access to a massive symphony of possible tunes, each one representing a different possible cosmos with its own laws and properties. Each distinct vacuum state corresponded to a different bubble universe, a different way that physical reality could be structured and organized. Some of these universes would be familiar, with physics similar to what we observe. Others would be utterly alien, barely recognizable, operating according to principles we can hardly imagine. Together, this enormous collection of possible universes formed what physicists began calling the multiverse landscape, or sometimes just the landscape, for short a vast space of possibilities within which our particular universe occupied one specific location. But the sheer size of the landscape, the incomprehensible number of possible universes it contained, deeply split the physics community into opposed camps with fundamentally different philosophical reactions. Leonard Susskind, one of string theory's founding figures and always intellectually fearless, embraced the landscape enthusiastically. He argued that this multiplicity of possible universes was not a bug in the theory, but rather a natural and even beautiful feature emerging from the mathematics. If string theory was correct, and if eternal inflation was correct, then combining these two frameworks naturally produced the landscape of bubble universes with varying physical laws. Steven Weinberg, a Nobel Prize-winning physicist whose work on the electroweak theory had helped establish the standard model of particle physics, saw the multiverse landscape as offering a practical, empirically grounded explanation for one of cosmology's biggest mysteries. This mystery concerned the cosmological constant, a parameter in Einstein's equations related to the energy density of empty space itself, sometimes called vacuum energy or dark energy. Observations showed that our universe possessed a cosmological constant with an extremely specific value, not zero, but incredibly close to zero, yet not exactly zero. This value was precisely small enough to allow galaxies and large-scale structures to form under gravity's influence, yet large enough to cause the universe's expansion to accelerate as dark energy gradually overcomes gravity on cosmic scales. The numerical value of the cosmological constant in our universe appeared finely tuned with extraordinary precision. Make it even slightly larger, and the universe would have expanded so rapidly that matter could never clump together to form galaxies, stars, or planets, just an eternally thinning soup of isolated particles. Make it substantially smaller or negative, and the universe might have collapsed back on itself long before stars could form or life could emerge. The fact that our universe possessed precisely the narrow range of values compatible with complex structures and living observers had long puzzled cosmologists. In a multiverse containing vast numbers of bubble universes with different physical parameters, Weinberg argued, this fine-tuning puzzle found a natural, almost obvious solution. Most bubble universes in the landscape would have cosmological constants far outside the narrow range compatible with structure, formation, and life. Those universes would be sterile, empty, devoid of observers who could wonder about cosmic parameters. But a small fraction of bubbles would, purely by chance, happen to have cosmological constants falling within the Goldilocks zone, not too large, not too small, but just right for galaxies and complexity to emerge. And we naturally, inevitably find ourselves in one of those rare universes simply because only those universes can produce observers capable of asking the question in the first place. This line of reasoning invoked what philosophers and physicists call the anthropic principle, the observation that any universe capable of being observed must necessarily possess properties compatible with the existence of observers. It's a form of selection bias, but on a cosmic scale. We shouldn't be surprised to find ourselves in a universe with a cosmological constant, allowing for structure formation, because we couldn't exist to be surprised in any other type of universe. In a vast multiverse landscape, life emerges only where conditions permit, and those are precisely the universes where conscious beings can wonder about cosmic constants and fundamental parameters. However, not everyone in the physics community reacted favorably to this landscape picture and its anthropic reasoning. Many prominent physicists recoiled strongly against the idea, viewing it as a betrayal of science's fundamental goals and methods. David Gross, another Nobel laureate whose work on quantum chromodynamics had been crucial for understanding the strong nuclear force, dismissed the landscape multiverse with barely concealed contempt. In public lectures and interviews, he declared forcefully, "This is not physics. This is giving up." His objection struck at what he considered the heart of the scientific enterprise. For Gross and like-minded critics, science's defining characteristic was its ability to make concrete, testable predictions that could be verified or falsified through experiment and observation. A proper physical theory should tell you what must happen given certain initial conditions, not simply catalog what might happen across an infinite range of possibilities. The landscape multiverse, in this view, abandoned predictive power entirely. If every possible universe exists somewhere in the landscape, then no observation could ever rule out the theory, because any unexpected result could simply be explained by saying, well, that's just the universe we happen to inhabit. The theory became unfalsifiable. And unfalsifiable theories, Gross insisted, weren't science at all. Lee Smolin, a theoretical physicist working at the Perimeter Institute in Canada and known for his critical thinking about foundational issues in physics, raised a complementary objection. He warned that the multiverse concept, particularly when combined with anthropic reasoning, stripped physics of its defining feature, falsifiability, the criterion that philosopher Karl Popper had identified as distinguishing genuine science from pseudoscience. Smolin argued that if every possible observation could be accommodated within the multiverse framework by appealing to the vast diversity of bubble universes, then the theory made no predictions that could genuinely be tested against reality. You couldn't prove it wrong, because any result, any measurement, any cosmic parameter value could be retroactively explained by anthropic selection within the landscape. If every possible universe existed somewhere in the vast multiverse ensemble, then no observation could ever disprove the theory's fundamental claims. The framework became too flexible, too accommodating, too capable of explaining anything after the fact. For Smolin, this represented a dangerous path for physics to follow, potentially leading the field away from its empirical foundations into pure mathematical speculation disconnected from observable reality. Science, he argued, advanced through the interplay of theory and experiment, through making predictions that nature could confirm or refute. The multiverse threatened to sever that crucial connection. The debate grew increasingly fierce and contentious throughout the 2000s and 2010 seconds, echoing older philosophical battles that stretched back centuries. Was reality fundamentally discoverable through observation and reason? Or were there aspects of existence forever beyond the reach of scientific investigation? Were humans, like the prisoners in Plato's famous cave allegory, confined to observing shadows on a wall, while the true nature of reality remained hidden behind us, forever inaccessible? These ancient philosophical questions found new expression in the modern debate over the multiverse landscape. Through all of this intellectual turbulence and controversy, Max Tegmark observed the unfolding chaos with a certain detached fascination, like a librarian watching scholars argue passionately in the reading room of a vast library. String theorists argued vigorously about extra dimensions and the landscape of vacuum states. Cosmologists engaged in heated debates about eternal inflation and bubble universes. Philosophers questioned whether any of this vast theoretical edifice could ever be empirically tested or verified. But Tegmark didn't align himself firmly with any particular faction or camp. Instead, he stepped back from the melee, observed the swirling confusion of competing ideas, and decided to bring order to the apparent madness. What the field desperately needed, Tegmark concluded, wasn't another voice joining the shouting match, but rather a clear organizational framework, a systematic way of thinking about the various multiverse proposals that could clarify the relationships between different ideas and help researchers understand what they were actually arguing about. He proposed what he called a hierarchy, a layered conceptual map of reality that attempted to make sense of the chaos by identifying distinct levels of multiverse, each progressively more radical than those below it. Level 1, Tegmark explained in papers and popular articles, was the simplest and most conservative multiverse level, the one closest to observational astronomy. Think of it as our own universe, extended to infinity, stretching endlessly beyond the observable horizon that light has had time to reach since the Big Bang. Far beyond what any telescope could ever detect, there exist more galaxies, more stars, more planets, and, inevitably given sufficient distance and time, more versions of Earth with more versions of you living out slightly or dramatically different lives. The fundamental laws of physics remain identical everywhere throughout Level 1. Only the initial conditions, the specific arrangements of matter and energy following the Big Bang, differ from place to place. It's like exploring an infinite library, where all the books follow the same grammar and syntax rules. But the specific words and stories vary endlessly. Maybe in one distant region beyond our cosmic horizon, you made a different choice this morning and wore blue socks instead of yellow. Maybe in another even more distant region, you chose an entirely different career path decades ago and now live a radically different life. These aren't speculations about alternate realities in some mystical sense. They're mathematical inevitabilities that follow from combining quantum mechanics with infinite space. Given infinity, every possible arrangement of matter permitted by the laws of physics must occur somewhere, and in fact must occur infinitely many times across the boundless expanse. Level 2 represented Tegmark's next step upward in the hierarchy, and it went considerably deeper than Level 1's simple spatial infinity. This was the realm that Andrei Linde's eternal inflation and Leonard Susskind's string theory landscape inhabited. Here, distinct regions of space stopped inflating at different times and formed separate bubble universes, each one potentially sealed off from the others by eternally inflating space between them. But these weren't merely copies or variations of our universe repeating at different locations. They were fundamentally different worlds, places where the basic rules governing physical reality could vary dramatically. The critical distinction between Level 1 and Level 2 comes down to what varies and what remains fixed. Level 1 keeps the laws of physics constant while varying the outcomes, like playing the same game repeatedly with different dice rolls each time. Level 2 goes further, actually changing the fundamental rules themselves, like switching from chess to checkers to an entirely different board game. One bubble universe might have gravity that's substantially stronger or weaker than ours. Another could feature a different number of spatial dimensions, with matter organized in ways we can barely imagine. Still, another might have a completely different set of fundamental particles and forces, making its chemistry and physics utterly alien. Some bubbles might be inherently sterile and lifeless, lacking the conditions necessary for complexity to emerge. Others might be ruled by physical laws so different from ours that stars never form, atoms never stabilize, or time itself behaves in unfamiliar ways. The difference between Level 1 and Level 2 is the difference between adjusting the volume knob versus replacing the entire stereo system with something fundamentally different. Level 1 tweaks parameters within a fixed framework. Level 2 transforms the framework itself, inventing entirely new rule systems for different regions of the multiverse landscape. To Tegmark, organizing these ideas into a clear hierarchy wasn't mere philosophical tidying or academic categorization for its own sake. It was a practical necessity for scientific progress. It provided a structured way to understand and discuss the vastness of possible existence, a cosmic filing system that could help researchers identify which ideas were genuinely distinct and which were merely different ways of describing the same underlying phenomena. It brought conceptual order to what had threatened to become an incoherent jumble of speculative proposals, each claiming to describe the ultimate nature of reality. Yet as Tegmark carefully placed inflation and string theory into his taxonomy of multiverse levels, sorting ideas onto conceptual shelves, he began to notice a conspicuous gap in the framework, a missing piece that none of the existing proposals adequately addressed. Inflation and string theory bubbles could explain, at least in principle, why different universes might have different values for fundamental constants and parameters. They provided mechanisms for generating variety in physical laws across the multiverse landscape, but they didn't directly address what Tegmark considered the strangest and most unsettling aspect of physical reality: the bizarre way quantum mechanics appears to allow every possible outcome to exist simultaneously in some sense, at least until a measurement or observation forces reality to commit to one specific result. This quantum puzzle had been sitting in plain sight, largely ignored or relegated to philosophical discussions since 1957, when it appeared in the doctoral thesis of a young graduate student at Princeton named Hugh Everett III. Everett's radical proposal had been dismissed, overlooked, or misunderstood by most of the physics community for decades, but it refused to completely disappear. And it was to Everett's long-ignored and often misunderstood idea that Tegmark and the multiverse framework would turn next, exploring what would become level 3 in the hierarchy. The autumn sunlight of the mid-1950 seconds slanted through ivy-covered walls at Princeton University, warming ancient stone courtyards where young physicists gathered in small groups to argue about the foundations of quantum theory in voices that mixed excitement with confusion. Inside the physics building, chalkboards were crowded with intricate equations representing decades of accumulated knowledge. Cigarette smoke, still ubiquitous in that era, hung thick in seminar rooms where the future of physics was being hammered out through vigorous debate and mathematical calculation. This was the late 1950 seconds, a period when the Second World War had ended just over a decade earlier, but its shadow still hung over scientific research. A new kind of tension filled the academic air, not the tension of military conflict, but the Cold War competition between superpowers, the nuclear arms race, and an atmosphere of secrecy and urgency surrounding anything related to atomic physics. Inside those hallowed lecture halls and laboratories, quantum mechanics reigned as the unchallenged theoretical framework for understanding the atomic and subatomic world. For roughly 30 years, since its initial development in the 1920 seconds, Erwin Schrödinger's elegant wave equation had successfully described the strange, wave-like behavior of particles at microscopic scales. The mathematics was beautiful, precise, and remarkably accurate at predicting experimental results. The Schrödinger equation was thoroughly deterministic in a certain sense. If you knew a quantum system's wave function at one particular instant, you could, in principle, calculate its complete evolution at any future or past time by applying the equation's rules. The wave function itself evolved smoothly and predictably according to well-defined mathematical laws. But there was a fundamental catch, a conceptual problem that everyone in the field recognized but few truly understood or felt comfortable discussing openly. Students learning quantum mechanics were taught that the wave function, despite evolving deterministically according to Schrödinger's equation most of the time, didn't actually continue evolving forever in that smooth, predictable way. Instead, something dramatic and mysterious happened at the moment of measurement. Whenever an observer attempted to determine a particle's position, momentum, spin, or any other quantum property. At that instant of measurement, according to the standard interpretation developed primarily by Niels Bohr and his colleagues in Copenhagen during the 1920 seconds and 30 seconds, the wave function collapsed. All the smooth, wave-like probabilities that had been evolving deterministically suddenly snapped into a single, definite outcome, like a spinning roulette wheel finally coming to rest on one particular number. Before measurement, the electron existed in a superposition of many possible states. After measurement, it occupied just one specific state, and all the other possibilities vanished instantaneously. This collapse wasn't described by Schrödinger's equation. It wasn't a natural consequence of the mathematical framework. It was an additional rule, a postulate tacked onto the theory after the fact, inserted by hand to make the theoretical predictions match what experimenters actually observed in laboratories. In the quiet hallways of Princeton's physics department, this fundamental inconsistency was like a hairline crack running through an otherwise flawless crystal, small enough that most people could ignore it most of the time, nearly invisible if you didn't look too carefully, but impossible for the sharpest and most philosophically inclined minds to completely overlook. Hugh Everett III was 26 years old in 1957, a graduate student working under the supervision of the legendary John Archibald Wheeler, one of the most creative and philosophically adventurous physicists of his generation. Wheeler had worked on the atomic bomb during the Manhattan Project, and had since become fascinated by the deepest questions about quantum mechanics and the nature of reality itself. Under Wheeler's mentorship, Everett felt empowered to ask bold, fundamental questions that more cautious students might have avoided. Everett posed what seemed like a straightforward but deeply subversive question. If the mathematics of quantum mechanics, specifically Schrödinger's equation, never actually includes or requires wave function collapse, why should we believe that reality itself involves such a collapse? What if the collapse rule, that mysterious, instantaneous snap from multiple possibilities to one actuality, was simply wrong? What if it was an unnecessary addition to the theory, inserted by physicists who felt uncomfortable with the full implications of the mathematics they had discovered? What if, Everett dared to suggest, you took Schrödinger's equation completely seriously and applied it to everything without exception, not just to individual particles, but to entire measuring devices, to human observers, to laboratory equipment, ultimately to the entire universe itself? If you followed that path consistently, if you refused to introduce the collapse postulate, and instead insisted that the wave function always evolved according to Schrödinger's deterministic equation, then something remarkable and unsettling emerged from the mathematics. Collapse never actually happened in physical reality. Instead, every possible outcome of every quantum measurement continued existing and unfolding in its own distinct branch of reality. Schrödinger's famous thought experiment about a cat in a box, simultaneously alive and dead until someone opened the box to check, was usually interpreted as demonstrating the absurdity of quantum superposition at macroscopic scales. But Everett said, what if it's not absurd? What if Schrödinger was more right than he realized? The cat wasn't somehow both alive and dead in some mystical, paradoxical state. Rather, the cat was alive in one branch of reality and dead in another separate branch. Both outcomes were real, both continued evolving, both played out their consequences. The universe itself split into multiple branches at the moment of quantum measurement, with each possible outcome realized in its own separate world. To make this somewhat more concrete without drowning in technical formalism, imagine flipping a quantum coin, a particle that can be in a superposition of two quantum states that correspond to what we might call heads and tails. In the standard Copenhagen interpretation, when you observe the coin, the wave function collapses and you see either heads or tails, with the other possibility simply ceasing to exist. But Everett proposed something radically different. The coin doesn't land on just heads or just tails. It lands on both simultaneously, but in separate, non-communicating branches of reality. Every time you flip that quantum coin, the universe itself branches. In one branch, you observe heads, and your experience continues from there. In another equally real branch, you observe tails, and that version of you experiences a different subsequent history. Both outcomes genuinely exist and play out their consequences, but in separate branches that can no longer interact or communicate with each other. Each version of you follows its own experiential thread, completely unaware of the other branches where different versions of you observe different outcomes. Now, extend this branching process to absolutely everything, every decision, every particle interaction, every quantum event throughout the entire universe. Each measurement, each quantum interaction, each moment when quantum randomness plays a role causes new branches to proliferate. Somewhere, right now, another version of you made a slightly different choice, spoke different words, or didn't exist at all because some crucial quantum event in your ancestors' history went differently in that branch. You personally don't feel these splits occurring because each version of you follows its own coherent thread of experience, its own continuous narrative, unaware of the countless other versions existing in parallel branches. To Everett, this picture seemed not only logically consistent, but actually more elegant than the Copenhagen interpretation. The universe wasn't a single film reel telling one definite story with all other possibilities erased at each measurement. Instead, reality was an endlessly branching tree of possibilities, all growing from the same quantum mechanical roots, each branch equally real and equally valid. There was no mysterious collapse, no special role for conscious observers, no arbitrary division between quantum and classical realm. There was only the smooth, deterministic evolution of the universal wave function according to Schrödinger's equation. naturally producing branching realities as its consequence. Everett carried his radical thesis across the Atlantic to Copenhagen, where the elderly Niels Bohr still presided over quantum physics like a philosophical patriarch guarding orthodox doctrine. Bohr had spent decades developing and defending what became known as the Copenhagen interpretation, the standard textbook view that wave functions collapsed upon measurement and that physics could only describe what we observe, not some underlying reality independent of observation. Bohr believed deeply that physics had to provide single, definite, communicable results, something you could measure, record in a laboratory notebook, and share with other scientists. The idea that measurements didn't produce single outcomes, but instead caused the universe to split into countless invisible copies, performing different experiments, sounded to Bohr like abandoning science for fantasy. Bohr listened to Everett's presentation with his characteristic stern patience, occasionally asking pointed questions, but ultimately remaining unconvinced. The Copenhagen establishment, which dominated quantum physics at that time, dismissed Everett's many worlds proposal almost entirely. It sounded too much like science fiction, too divorced from experimental practice, too metaphysically extravagant. How could you possibly have countless invisible universes branching off at every moment? Where did all that reality come from? Didn't this violate conservation of energy or some other fundamental principle? The questions came thick and fast, and few physicists were willing to take the idea seriously. Frustrated by the hostile reception his work received in the physics community, seeing no path forward for an academic career built on ideas that senior physicists rejected or ridiculed, Everett made a fateful decision. He abandoned academic physics entirely and joined the Pentagon's network of defense-oriented think tanks, accepting a position working on nuclear war planning and game theory at the height of Cold War tensions. There's a profound and tragic irony in that career choice. In his theoretical work, Everett had proposed that reality endlessly branched, creating infinite variations and possibilities, countless worlds where different choices played out. But in his day job at the Pentagon, he spent his time calculating scenarios where human civilization could end in a single catastrophic flash of thermonuclear fire, modeling the annihilation of possibilities rather than their multiplication. Everett never returned to academic physics. He drank heavily as the years passed, grew increasingly disillusioned with both his career and his abandoned theoretical work, and died in 1982 at just 51 years old, his health destroyed by decades of alcohol abuse and chain smoking. In some alternate branch of the quantum multiverse, perhaps there exists a reality where Everett lived to see his radical ideas vindicated, where he received recognition and acclaim during his lifetime, where his theoretical insights were celebrated rather than dismissed. In our branch of reality, tragically, he died, ignored, and largely forgotten, his revolutionary thesis gathering dust in academic libraries. For nearly 2 decades after Everett's death, his paper on the many worlds interpretation remained largely ignored by mainstream physics, occasionally mentioned as a curious footnote or philosophical curiosity, but rarely taken seriously as a genuine physical theory. Then, beginning in the 1,980 seconds and accelerating through the 1,990 seconds, physicists like Wojciech Zurek, Dieter Zay, and others began reviving and refining Everett's framework through work on what became known as quantum decoherence. Decoherence provided a rigorous mathematical explanation for why Everett's branching universes don't interfere with one another, why we never observe superpositions at macroscopic scales, even though they might exist in some sense. Decoherence theory explained that as soon as any quantum system interacts with its surrounding environment with air molecules, background radiation, thermal photons, or even the atoms in a measuring device, the delicate quantum superposition that might have allowed different outcomes to interfere with each other breaks apart almost instantaneously. Each possible outcome continues evolving on its own independent trajectory, but the different branches become effectively isolated from each other, unable to recombine or influence one another. The mathematical description is complex, but the basic idea is relatively straightforward. Think of perfectly formed ripples spreading across a smooth, undisturbed glass of water. When the ripples from different sources meet, they interfere with each other in beautiful, intricate patterns of reinforcement and cancellation. This is the quantum regime where superpositions are maintained and different possibilities can interact. Now imagine tossing a handful of sand into that water. The ripples immediately scatter and fragment into chaotic, isolated puddles that can never meet again to create interference patterns. That's decoherence in action. The delicate quantum correlations that connected different branches of the wave function get scrambled by interaction with the environment, effectively separating the branches so completely that they might as well be different universes. This theoretical development gave Everett's decades-old ideas genuine scientific substance. It wasn't just philosophical speculation anymore. Decoherence provided a concrete physical mechanism explaining why we don't see macroscopic superpositions in everyday life, not because wave functions mysteriously collapse, but because environmental interactions destroy quantum coherence so rapidly that classical behavior emerges naturally from quantum laws. Famous quantum experiments, like the double-slit test, where particles seem to go through two paths simultaneously, began to look different when viewed through the Everett lens. In the traditional interpretation, physicists said the particle existed in a superposition going through both slits, then collapsed to a definite path when observed. In Everett's view, refined by decoherence theory, the particle genuinely went through both slits, but in different branches of the universal wave function. We only ever experience one branch because decoherence has isolated the branches from each other, but the other branch is just as real, just as physical. It's simply forever separated from our experiential timeline by the branching structure of quantum reality. Or think of it using a musical analogy that Tegmark particularly enjoyed. Imagine listening to a symphony orchestra where all the instruments play together in perfect harmony. The sound waves from different instruments blend and interfere, creating one coherent, beautiful musical experience. That's quantum coherence. Different possibilities existing in a coordinated superposition. But the moment someone opens a door to the noisy street outside, chaos floods in. The symphony gets drowned out by traffic noise, shouted conversations, wind, car horns, random environmental sound. The musical notes are technically still there, still vibrating in the air, but the interference from everything else, all that environmental noise, separates and scrambles the sound so completely that you can no longer hear the orchestra as a unified whole. The coherent symphony has fragmented into noise. That's essentially what happens in the quantum world whenever particles interact with their surroundings. When microscopic quantum systems encounter macroscopic environments filled with countless air molecules, photons, electromagnetic fields, and thermal vibrations, they lose their delicate quantum coherence almost instantaneously. The wave function doesn't mysteriously collapse into nothing. Instead, it decoheres, splitting into separate outcome branches that continue evolving independently but can no longer hear or influence each other. Like separated orchestra sections playing in soundproof rooms, Tegmark found this framework intellectually satisfying and deeply illuminating. To him, decoherence wasn't mystical or paradoxical. It was fundamentally practical, a straightforward consequence of quantum mechanics applied consistently to large, complex systems. It explained clearly and precisely why we don't encounter cats that appear to be simultaneously alive and dead, or coins that seem to show both heads and tails at once. Each version of the macroscopic world, alive cat, dead cat, heads, tails, continues playing out its own physics, but in its own isolated concert hall of reality, separated by decoherence from all the other concert halls where different outcomes unfold. When Tegmark first encountered Everett's work decades after it was written, he didn't see a crazy fantasy or a departure from serious physics. He saw physics doing what it always does when taken to its logical conclusion, following its own mathematical logic wherever it leads, regardless of whether the destination feels comfortable or intuitive to human minds. If the mathematics of quantum mechanics says that all possible outcomes persist and evolve according to Schrödinger's equation, then somewhere, somehow, in some rigorous sense, they do persist. The challenge for physicists wasn't to dismiss this conclusion, but to understand it properly and work out its implications. Tegmark's particular genius lay not just in understanding the physics behind Everett's proposal, but in recognizing how it fit into his larger framework, organizing different types of multiverse. He placed Everett's branching quantum realities as level 3 in his grand hierarchical system. Level 1, recall, was the infinite spatial universe, where only initial conditions varied while laws remained fixed. Level 2 encompassed the inflationary bubble universes, with potentially different physical constants and laws emerging from string theory's landscape. Level 3 became Everett's quantum multiverse, representing something conceptually distinct from the previous two levels. Here's the crucial detail that many people misunderstood about Level 3. It doesn't add universes on top of levels 1 and 2. It doesn't unnecessarily multiply infinities or stack separate realities in some crude way. Instead, Level 3 shows that within any given universe described by quantum mechanics, whether that's a Level 1 repetition or a Level 2 bubble, every quantum possibility plays out in its own branch of the wave function. The universal wave function evolves smoothly and deterministically according to Schrödinger's fundamental equation, and each quantum measurement doesn't collapse possibilities, but rather causes them to decohere into independent branches. Think of it like playing a complex role-playing video game, one of those sprawling open-world adventures where player choices genuinely matter and shape the narrative. You reach one of those crucial decision points that the game designers have built into the story. Do you spare the captured enemy or execute them? Do you side with the mages or the Templars? Do you take the hidden path through the mountains or the obvious route through the valley? You make your choice based on your character's values and your playing style, and the game's story branches accordingly, continuing forward from that decision point. In your particular playthrough, your unique experience of the game's narrative, you chose mercy, and the captured enemy lived, becoming an ally later in the story. But somewhere in another saved game file that you'll never see, another version of your character made the opposite choice, drawing their sword instead of showing mercy, and the story branched in a completely different direction with different consequences. Both storylines exist as valid possibilities within the game's code. Both are internally consistent. Both follow the same underlying game mechanics and rules. You just happen to experience one particular path at a time, one continuous narrative thread, while other equally valid paths remain unexplored in your playthrough. Everett's Level 3 multiverse works similarly, but applies to physical reality rather than video games. Every quantum fork in reality, every moment where quantum mechanics allows multiple outcomes, is like one of those crucial decision points. The universe doesn't randomly select just one outcome and erase the others. Instead, it branches, with each outcome continuing to evolve in its own separate thread of reality. You experience one continuous timeline because decoherence keeps the branches separated, but all the other branches are equally real, equally physical, following the same quantum mechanical rules you experience. This idea of branching quantum realities, of infinite unseen versions of ourselves, living out different choices and experiencing different outcomes, didn't remain confined to physics papers and academic conferences. It leaked powerfully into popular culture, particularly into cinema and television, where storytellers found the concept irresistible. Directors and screenwriters fell deeply in love with the what-if logic embedded in Everett's many worlds interpretation. Every fork in a character's story, every pivotal choice, could be portrayed as a literal split in reality rather than just a narrative device. You encounter this quantum multiverse concept everywhere in contemporary media. Consider the film Everything Everywhere All at Once, which won multiple Academy Awards and became a cultural phenomenon. The protagonist, Evelyn Wang, is a middle-aged woman struggling to run a failing laundromat, dealing with a difficult marriage, a rebellious daughter, and an overwhelming tax audit. Suddenly, she's thrust into conscious awareness of the quantum multiverse, experiencing countless other versions of her life, across infinite branches where every choice she made or didn't make created entirely different realities. In one branch, she became a legendary kung fu master, her life dedicated to martial arts perfection. In another, she's a glamorous movie star, living in luxury and fame. In yet another bizarrely comic branch, she and her husband have hot dog sausages for fingers, living in a reality with fundamentally different biology. Each branch is absurd, emotionally resonant, and deeply human in its own way. The film takes Everett's austere quantum mechanical concept and transforms it into a meditation on choice, regret, possibility, and meaning. All those infinite versions of you, scattered across the branching timelines, all struggling to find purpose and connection in their particular reality. Or examine Mr. Nobody, one of the most philosophically profound and haunting cinematic explorations of the multiverse ever created. The film opens with a deceptively simple human dilemma that everyone can relate to. A young boy named Nemo stands on a train platform as a train is about to depart, carrying his mother away. His parents are separating, divorcing, splitting his childhood world in two. His mother steps onto the train, preparing to leave. His father remains behind on the platform. and young Nemo hesitates in agonizing indecision, torn between two impossible choices, two competing loyalties, two different futures. Does he run after his mother and board the moving train? Or does he stay with his father on the platform? In that single heartbeat of childhood indecision, that one frozen moment of hesitation, reality itself fractures. According to quantum mechanics, from that pivotal point onward, the film doesn't follow just one linear life. It follows all of them simultaneously, showing us the branching structure of Nemo's possible lives. We watch him grow up in parallel quantum worlds, each stemming from that single decision point. In one branch, young Nemo runs after his mother, grows up in her household, and becomes a wealthy businessman trapped in an emotionally empty marriage, materially successful but spiritually hollow. In another branch, he stays with his father, becomes a drifter and wanderer, searching for meaning in transient experiences, never quite finding a place to belong. In yet another timeline, he becomes a scientist obsessed with understanding time itself, chasing the deepest mysteries of temporal physics, as if seeking some way to reconcile or understand all his possible lives. Each distinct timeline unfolds with its own internal logic, showing how one pivotal childhood choice creates completely different versions of Nemo's life. Different careers, different relationships, different personalities even. The profound beauty of Mr. Nobody lies in its refusal to privilege any single timeline as the real or correct one. All of them exist simultaneously in the film's narrative structure, overlapping and diverging like quantum possibilities that never fully collapsed into a single classical outcome. All these lives are equally valid, equally real within their own branches. By the film's enigmatic conclusion, the elderly Nemo himself seems to realize there is no single fixed version of his identity, no one true life he lived. Instead, he exists as a superposition of possibilities, a web of different selves endlessly branching out across the quantum landscape of choice and chance. It's a deeply poetic interpretation of Everett's physics. The universe, the film suggests, doesn't erase the paths you didn't take, the choices you didn't make, the lives you didn't live. It preserves them all. Somewhere in the branching structure of quantum reality, every version of you continues existing, living out the roads not taken in your particular timeline. Somewhere, that alternative you is still pursuing the dream you abandoned, still in the relationship you ended, still living in the city you left behind decades ago. Hollywood embraced this concept enthusiastically because it resonates with universal human experience. Everyone wonders about roads not taken, about the job offer they declined, about the person they never called, about the opportunity they let slip away out of fear or circumstance. Everett's quantum multiverse offers an unexpected form of comfort. It suggests that none of those alternate paths are truly lost or erased from existence. They're all still unfolding somewhere in the vast branching structure of reality, each in its own quantum timeline, each as real as the life you're currently living. Somewhere in the quantum multiverse, instead of walking away, you actually gathered the courage to tell your high school crush how you really felt. And maybe in that particular branch, you ended up marrying them, building a completely different life together. Somewhere else, instead of staying in the safe 9-to-5 job, you took the terrifying leap of faith to start your own business. And perhaps in that timeline, another version of you is living with completely different challenges and rewards than you experience now. It's simultaneously haunting and comforting, the idea that every what-if you've ever imagined might not be mere fantasy, but actual reality playing out in another branch of the quantum tree. Not everyone in the physics community was satisfied with this picture, despite its mathematical elegance and its success at avoiding the measurement problem that plagued the Copenhagen interpretation. Some physicists argued that while Everett's branching framework solved the problem of wave function collapse, it left other fundamental questions conspicuously untouched and unanswered. Why do the constants of nature have the particular values we observe rather than others? Why does time flow in one direction? Why does space have 3 dimensions rather than 2 or 17? Everett's many-worlds interpretation explained how quantum possibilities branched, but it didn't explain why the underlying laws creating those branches had the specific mathematical form they do. That's when new theoretical rebels stepped forward with even more ambitious proposals that pushed beyond Everett's framework. In 1992, Lee Smolin, working at the Perimeter Institute for Theoretical Physics in Canada, proposed something radically different that borrowed concepts from biology: cosmic natural selection. Smolin suggested that universes might actually reproduce, like organisms, creating offspring universes with slightly modified physical laws. Every black hole, he argued provocatively, might function as a kind of cosmic womb, a birthing chamber for a daughter universe. According to Smolin's speculative but mathematically detailed proposal, when matter collapses into a black hole and forms a singularity, conditions might allow a new region of space-time to bud off, creating an entirely separate universe on the other side of the black hole's event horizon, forever causally disconnected from the parent universe. As this new baby universe is born from the black hole, the fundamental constants of physics, things like the mass of the electron, the strength of gravity, the fine structure constant might shift slightly, introducing small, random variations similar to genetic mutations in biological reproduction. Over vast cosmic timescales spanning countless generations, Smolin argued, a kind of natural selection would operate on these reproducing universes. Universes whose physical constants favor the production of many black holes would generate more offspring universes, passing on their physics to daughter universes with slight modifications. Over time, the multiverse would evolve toward configurations that are particularly good at making black holes, just as biological evolution tends toward organisms well adapted to reproduction in their environments. Instead of finches with different beak shapes adapting to different island environments, we'd have universes with different physical constants adapting to maximize black hole production. Smolin often positioned himself intellectually against the mainstream tide of string theory and the anthropic reasoning that many physicists use to explain fine-tuning. His cosmic Darwinism was intentionally provocative, admittedly difficult to test empirically, but it offered an intriguing extension of Everett's branching concept into the realm of biological metaphor. Instead of branches created by quantum measurements, Smolin envisioned branches created by black hole reproduction, with variation and selection operating across cosmic generations. Roger Penrose, the brilliant Oxford mathematician renowned for his groundbreaking work in general relativity and his collaborations with Stephen Hawking on black hole physics, offered yet another radically different vision of cosmic cycles that departed from both inflation and Smolin's biological analogy. Penrose was skeptical of inflation theory, unconvinced by its assumptions, and he certainly didn't embrace Smolin's reproductive cosmology. Instead, beginning in the 2000s, Penrose developed what he called conformal cyclic cosmology, or CCC for short. In Penrose's mathematical framework, our universe represents just one aeon in an infinite temporal sequence of universes succeeding one another, like beads threaded on an endless cosmic necklace. As time stretches infinitely forward in any given aeon, all matter eventually decays through various quantum processes. Black holes slowly evaporate through Hawking radiation over incomprehensibly long timescales, and ultimately only radiation remains a featureless, maximally dispersed sea of massless photons filling an exponentially expanding void. Here's Penrose's key mathematical insight. Once you properly account for the relevant physics and apply certain geometric transformations, that final state of one aeon, an infinite, featureless expanse filled only with radiation, becomes mathematically indistinguishable from the initial state of a new Big Bang beginning the next aeon. Through a conformal transformation that rescales geometric relationships while preserving certain fundamental structures, the infinitely stretched ending of one universe maps directly onto the compressed, hot beginning of the next. In this way, universes don't branch outward like a tree or reproduce like organisms. Instead, they flow into one another cyclically like waves, each aeon emerging from the ashes of the previous one in an eternal cosmic cycle. Penrose sometimes compared his vision to the ancient myth of the phoenix, that legendary bird that burns to ash, only to rise again, reborn from its own remains. Each universe lives out its full cosmic lifespan, gradually dissipating into thin radiation as entropy inexorably increases. But that state of maximum entropy and minimal structure somehow seeds the violently energetic, low entropy beginning of the next cosmic cycle. The multiverse in Penrose's picture doesn't expand spatially or split quantum mechanically. It cycles temporally, endlessly dying and being reborn through an infinite sequence of cosmic ages. These diverse visions, Smolin's reproductive cosmology borrowing from Darwinian biology, Penrose's cyclic conformal geometry leaning on sophisticated mathematics and general relativity, were both, in their own ways, intellectual heirs to Everett's fundamental insight about reality's multiplicity. Each pushed the boundaries of what a multiverse could mean. Each offered a distinct logic of multiplication, showing how one universe might generate many. Reality, all these frameworks agreed, doesn't settle contentedly for just one universe. Through various mechanisms, quantum branching, eternal inflation, black hole reproduction, cyclic rebirth, existence proliferates, multiplies, extends itself beyond the single observable cosmos we inhabit. Tegmark systematically gathered all these proposals under his comprehensive shelving system, his hierarchy of multiverse levels. Whether universes branched through quantum decoherence, bubbled through eternal inflation, or cycled through conformal transformation, they all shared a fundamental logic of multiplication, a refusal to limit reality to a single instantiation. But for Tegmark personally, even this rich taxonomy of multiverse types wasn't quite enough. Quantum branching explained how all possible outcomes existed. Inflationary bubbles explained why fundamental constants might vary from region to region. Cyclic cosmologies suggested possibilities for eternal rebirth and renewal. Yet all of these frameworks, sophisticated and mathematically rigorous as they were, still fundamentally belonged to the realm of physics. They were ultimately about particles, fields, space-time geometry, quantum wave functions. Tegmark began to wonder whether physics itself, rather than being the bedrock of reality, might be just one particular expression of something deeper, something more fundamental underlying all physical law. What if reality at its deepest level wasn't built from particles, fields, or waves at all, but from pure mathematics itself? What if the universe wasn't merely described by mathematics, but actually was mathematics in some profound sense? That question would open the door to Tegmark's most radical and philosophically controversial level yet. Level 4, where not just universes, but the very laws of mathematics themselves become real, where every consistent mathematical structure exists as its own universe. But before we can understand Level 4 properly, we need to appreciate Tegmark's personal intellectual journey and the specific vision that led him to this ultimate conclusion about the nature of existence. By the time the 2000s arrived, Max Tegmark had already established a solid reputation for himself at MIT as a serious cosmologist and theoretical physicist. Colleagues respected his technical work analyzing data from cosmic microwave background experiments and refining inflationary models. But they also whispered about his apparent taste for bold, speculative ideas that pushed far beyond conventional boundaries. Students affectionately called him Mad Max, not because he was sloppy with calculations or careless about mathematical rigor, but because he seemed utterly fearless in asking the kinds of deep questions that made more cautious physicists uncomfortable. Where most cosmologists focused on tightening theoretical models of inflation, extracting precise parameter values from satellite data, or refining our understanding of dark matter and dark energy, Tegmark kept circling back to more fundamental philosophical questions. He wanted to understand not just how the universe behaved, but what kind of thing it fundamentally was at the deepest possible level. His answer, when he finally articulated it fully, shocked even the most speculatively inclined corners of the physics community. The universe is mathematics. Not described by mathematics, not governed by mathematical laws imposed from outside, but literally, ontologically mathematics itself. Tegmark laid out this claim most clearly and comprehensively in his 2014 book, Our Mathematical Universe: My Quest for the Ultimate Nature of Reality. The central thesis was blunt, uncompromising, radical. Mathematics doesn't merely describe physical reality from some external vantage point, like a map representing terrain. Mathematics is reality. The Schrödinger equation governing quantum mechanics, Einstein's field equations describing curved space-time and gravity, Maxwell's equations governing electromagnetism and light. These aren't useful human inventions that happen to track how nature works with remarkable accuracy. According to Tegmark's mathematical universe hypothesis, these equations are themselves the fundamental bedrock of existence. The universe isn't constructed from atoms or particles or quantum fields or even energy as we normally conceive it. At the deepest level, reality is built from mathematics itself, pure mathematical structure with no additional substance required. This claim, which Tegmark called the mathematical universe hypothesis, or MUH for short, states that every possible mathematical structure exists not as an abstraction in some platonic realm of forms or in mathematicians' minds, but as a real, physical universe playing out its own internal logic. Our particular universe, with its 3 spatial dimensions, 1 temporal dimension, and specific laws, like quantum mechanics and general relativity, is simply one mathematical structure among literally countless others scattered across an infinite landscape of mathematical possibility. Somewhere else in this abstract landscape, there exist universes with 4 spatial dimensions and no time dimension at all. Or universes where arithmetic doesn't follow our familiar rules of addition and multiplication, but instead operates according to strange modular systems or non-commutative algebras. Or universes with entirely different topological structures, different symmetries, different fundamental organizing principles. If a mathematical structure can be rigorously defined, if it's logically consistent within its own framework, then according to Tegmark, it exists as a universe somewhere in the grand multiverse ensemble. This makes the mathematical universe hypothesis perhaps the most radically inclusive multiverse proposal ever seriously considered by physicists. It doesn't just multiply universes, it includes literally every conceivable universe that can be described mathematically, which potentially means infinitely many different types of reality, each following its own mathematical logic. What makes this claim genuinely radical rather than merely speculative is how it completely dissolves the traditional boundary between physics and mathematics that scientists had always maintained. Physicists traditionally treated their equations as models, as useful representations of some underlying substance. They believed the universe possessed a fundamental physical reality made of particles, or fields, or strings, or something tangible in mathematics was merely the best tool humans had discovered for describing that pre-existing physical stuff. Mathematics was the map. Physics was the territory being mapped. Tegmark stripped away that comfortable distinction entirely. There is no hidden layer of physical stuff lurking beneath the mathematical description. The mathematics doesn't point to something else more fundamental. The mathematical structure is the thing itself, the ultimate reality. There's nothing else there, no additional ontological layer requiring explanation. When you've specified the mathematical structure completely, you've specified everything there is to know about that universe. The map and the territory are identical. In the end, our journey through the multiverse, from Hubble's distant galaxies to quantum branching to mathematical existence itself, reveals a cosmos far stranger and vaster than our ancestors ever imagined. Whether reality truly consists of infinite repetitions, bubble universes, quantum branches, or pure mathematical structures, one thing seems certain: we are not alone. Our universe is just one voice in an infinite cosmic chorus, singing its own unique song in the grand symphony of existence.